Scientists have explained the unusual behavior and composition of Comet 3I Atlas. Astronomers have determined where interstellar objects come from. It has been revealed what kind of meteor flew over Russia. We will discuss these and other amazing space discoveries right now. Today, half of astronomical news is in some way dedicated to Comet 3I Atlas, and that's unavoidable. It truly is a unique object, only the third one from interstellar space. What's new? For example, from the very beginning we were surprised that its composition contains more carbon dioxide ice, that is C2O ice, than water ice, H2O ice. Usually, our comets are dominated by water ice with a small amount of C2O, but this one has more carbon dioxide ice. In the solar system, this is not uncommon. For instance, when we look at the polar caps of Mars, especially towards the end of the Martian winter, a huge polar cap grows. What is it made of? In summer, it's small and made of water ice. Water ice freezes when temperatures drop below zero. But by the end of winter, during the long polar night lasting half a year, temperatures fall below -150 degrees Celsius, sometimes even -170, and a large skirt of carbon dioxide ice, C2O, forms. There is a lot of carbon dioxide in the Martian atmosphere, and at low temperatures it freezes. So this is not rare. Why did this comet present us with such a gift in the form of carbon dioxide? Probably because it formed far from its star. Objects close to a star are held tightly by the star's gravity and don't go anywhere, just like planets near the sun live and don't plan to fly away. But those objects far from the sun can be nudged by the gravity of a passing star or even the galaxy as a whole, which is also massive. Our outer objects can leave the solar system. They formed where it was cold, far from the sun, so their composition shouldn't match that of the inner solar system. The same likely happens in other planetary systems. They lose their outer objects. Those that are lost wander through the galaxy and sometimes fly into our system. We then receive a unique composition from them. They lived far from their star, where not only water but other volatile substances like methane and carbon dioxide froze. Carbon dioxide is quite abundant in interstellar material, but it turns out there are other ways for the chemical evolution of an interstellar object's composition. A study by several astrophysicists explored why Comet 3I Atlas has several times more carbon dioxide ice than water ice. Their calculations showed that this comet wandered through the galaxy for billions of years. Conditions in the galaxy between stars are different from those near stars. For example, near the sun, mostly solar material flies between planets, what we call the solar wind. Essentially, this is plasma lost from the sun's atmosphere. Remember what the sun looks like during a total solar eclipse. The moon covers the bright solar disk, and around it, we see the corona. What is the corona? It's gas that slowly, or not so slowly, at about 1,000 kilometers per second, leaves the sun's surface. It moves away from the sun and becomes more diffuse, but for a long time, even at great distances, it remains denser than the interstellar medium within the galaxy. So, the solar wind, the solar plasma, pushes away and prevents external gas from entering the central part of the solar system. This is our material. Moreover, the solar wind is plasma, a collection of electrically charged particles. Electrons and protons fly separately. This conductive medium carries magnetic fields traveling through the solar system. The plasma, as it moves away from the sun, drags the magnetic field with it, acting like a net that squeezes out foreign, also electrically charged gas from the inner solar system, keeping it out. Therefore, radiation conditions inside the solar system are milder because solar radiation is relatively soft. It can be absorbed by a spacecraft while a few decimeters thick. But cosmic rays traveling through the galaxy, born from supernova explosions, are much more intense, energetic, and deeply penetrating. They are not easy to shield against. While the comet wandered through the galaxy, it was bombarded by much harsher interstellar radiation. What did this lead to? First, a solid shell formed around the comet's icy core. It can be called a crust, as it usually is. It consists of fairly complex chemical substances synthesized under the influence of cosmic radiation. Light elements like hydrogen, carbon, nitrogen, and oxygen formed more complex organic substances. They usually have a reddish tint and covered the surface of this icy nucleus with a thick crust. By the way, we usually see a thinner crust on our comets, but it's easily broken by gases that evaporate and escape to the comet's surface, breaking the crust and then flying off into the comet's tail. But apparently, the crust of this new interstellar comet was thicker, according to calculations, several meters thick, maybe up to 5 meters. This is protection against radiation. We dream of spacecraft with walls of similar thickness to protect our astronauts. When this comet entered the solar system, heated by solar rays, it cracked this crust. Easily evaporating substances, primarily CO2, carbon dioxide, began to evaporate. Breaking through the crust, it enveloped the comet's nucleus with a coma, a temporary atmosphere. Then, under the influence of sunlight and solar plasma, a fairly noticeable tail has now formed. But radiation continued to work both inside and outside the solar system, producing a chemical cycle inside this nucleus. It broke down, dissociated, and destroyed complex organic molecules from the crust, again forming carbon monoxide, CO, and carbon dioxide, CO2. So the composition was continuously restored. Water gradually gave up its oxygen, carbon atoms took it, and an excess of carbon dioxide relative to water molecules resulted. So overall, it's a fairly clear explanation for why this comet has such an original chemical composition. First, it likely formed far from its star. Second, during its journey through the galaxy, it acquired a new chemical composition, at least in the outer part of its icy nucleus. By the way, the comet has already passed the most interesting region of the solar system. It recently approached the Sun, past perihelion, the closest point to the Sun in its orbit, heated up maximally by its rays, and now shows much brighter effects, ejecting gas from itself. For several days, literally 3 or 4 days before this recording, astronomers began to notice it emerging from behind the Sun. For the past 2 weeks, we couldn't see it because the Sun was blocking it. It passed close by the Sun, but now observations are starting again. So far, only radio astronomers are managing this issue. The fact is, the Sun doesn't interfere much with a radio telescope. It does cause some radio interference, but once the comet moves a few degrees away from the Sun, it becomes accessible to radio telescopes. The largest such complex of radio telescopes on Earth in South Africa has already detected interesting features in this comet. It will continue to move away from the Sun, and ground-based telescopes will join in again. There is even hope that one interplanetary spacecraft can accidentally fly through the tail of this remarkable comet. On board this spacecraft, which is primarily sent to study Jupiter's moons, especially Europa, it can perform precise chemical, even isotopic analysis of the material in the comet's tail. The spacecraft has a mass spectrometer, an instrument that counts atoms by their chemical type, even isotopic type. It can very accurately determine the composition of any gas. There is hope that the gas density in the comet's tail will be sufficient for this instrument to capture and count atoms of different chemical elements, even isotopes. This is very interesting because we are essentially receiving a gift from another planetary system. Until now, we were excited when meteorites fell to Earth, saying nature gave us material from the solar system. They came on their own, and now they are also arriving from other planetary systems, from the depths of the galaxy. It's not out of the question that some could come from other galaxies, though that's much farther. Since we've started discovering an incredibly large number of visitors from within our galaxy, it's possible something could come from the Andromeda Nebula or the Large Magellanic Cloud. That would be truly fascinating. We must keep searching. Just think, 100 years ago, space was science fiction. In historical terms, it's been an instant. What achievements has humanity reached? We launch orbital telescopes, live in orbit, and plan bases on the moon. The same can be said for the financial sector. Now we have debit cards with favorable terms and convenient mobile apps. What was unimaginable a century ago is now in everyone's hands. You can open such a card for free at Ozone Bank. Maintenance, transfers, deposits, and withdrawals at partner ATMs are also free. You can make payments anywhere, in restaurants, supermarkets, and any stores. Additionally, millions of items for 1 ruble on Ozone or cashback up to 25% in selected categories. Get an Ozone Bank card via the link in the description and enjoy the financial achievements of the 21st century. Now, if we're talking about where they come from, let's look at another study. It's quite simple but very useful. The topic is this: 3 times in the history of astronomy, in the 17th, 19th, and now in 2025, we've noticed foreign objects, asteroids or comets flying through our solar system far from Earth. But it's not impossible that something has fallen to Earth. The search for such objects has been taken up by the now famous, well-known American astrophysicist Avi Loeb, who often hints that interstellar visitors might not be coming for no reason. Perhaps they are ships of artificial or natural intelligence. Avi Loeb, you may have seen him squinting when he talks about this, likely a bit of light self-promotion. But he's not just giving hints to journalists. He works in this direction as a scientist. He set a goal. Among the huge number of meteors that streak through our atmosphere every night, burning up as bright falling stars, were there any that came from far away? How to check? Quite simple. Look at their speed. If slow, they're ours. If fast, faster than the sun could hold them at that speed, meaning faster than Earth's second cosmic velocity, then they're not ours. They flew in and accidentally hit Earth's atmosphere. He began searching and found something. He looked through archives of observations made by American satellites monitoring intercontinental missile launches. In any major country like the US, China, or Russia, there are satellites looking down on Earth, recording bright flashes in the atmosphere. What if it's a foreign missile starting its journey and could pose a danger? They recorded in 2014 that a body, probably about a meter in size, from half a meter to a meter, entered Earth's atmosphere. Judging by its motion, its speed was clearly higher than what would allow it to be a member of the solar system. It disintegrated. Such small ones usually don't reach the ground, but when it broke apart, some small particles could still fall to Earth. Such fine meteoritic dust, as we call it, doesn't completely burn up and often invisibly coats the land and ocean. Avi Loeb, tracing the trajectory of this object, saw that it should have fallen into the Pacific Ocean near New Guinea. What did this persistent scientist Avi Loeb do? He found a sponsor who chartered a small yacht for him, and Avi Loeb with a team went to where this interstellar object, in his view, should have fallen. They began probing the ocean floor with magnets and found some small spheres, called spherules, millimeter-sized metallic balls. Chemical analysis showed, as Avi Loeb reports, I can't vouch for this, that the composition of this metal is completely non-terrestrial. We don't smelt such material here. This was a hint that a small fragment, let's say, was part of some extraterrestrial device, maybe a satellite. We also have satellites of similar size. They could also leave the solar system. Right now, 2 Voyagers, 2 Pioneers, and New Horizons are flying. These are 5 of our spacecraft leaving the solar system. Couldn't a foreign one also fly into our system? That's what Avi Loeb thinks. And why not? This is also a hint that we should expect such visitors right in Earth's atmosphere. This work was just published in an archive. It belongs to 4 astronomers from different countries: the US, Serbia, Italy, and Spain. Together, they created a mathematical model. Nowadays, computers are so powerful that amazing models can be made. They simulated 100 billion random particles, interstellar meteorites that should be flying around the solar system, as the nearest stars around us fly, because most likely they lost this space debris. Then they simulated Earth's motion among these particles and saw where they most often come from, which part of the globe they hit, and at what speed. But this is, so to speak, work for the future. Where to expect them, in which seasons, in which parts of the world, in the form of meteors, cosmic visitors from the depths of the galaxy. Out of 100 billion model particles, about 10,000 hit the mathematical Earth. The rest just flew by. The conclusions were, first, the flow of these meteorites should be maximum from the direction Earth is flying. That's obvious. If random objects, like people in a crowd moving randomly and you walk through the crowd, who do you bump into? Those coming towards you, and you are moving towards them. Earth demonstrates 2 main motions. First, the entire solar system flies in a certain direction in the galaxy. Second, Earth around the Sun changes its flight direction throughout the year, and its speed is also quite high. All this was taken into account. Where is the solar system flying with Earth? First, it moves in the plane of the galaxy around the galactic center at a very high speed, about 220 kilometers per second. The nearest stars also move at roughly the same speed. We are flying around the galactic center surrounded by them. This motion can be disregarded, but relative to the nearest stars, our solar system also moves. It flies at about 30 kilometers per second towards the constellation Hercules. That's where astronomers say the apex of solar motion is located, the direction the solar system is moving. This motion is constant. It doesn't change year to year. But during the year, Earth moves in one direction at 30 kilometers per second in its orbit, then in another direction. So, its motion sometimes adds to the Sun's, resulting in 60 kilometers per second, or subtracts from it, so Earth practically stops in space. The Sun flies, and Earth moves in the opposite direction at the same speed. All this was considered. Naturally, it turned out that the main flow of meteorites hitting Earth comes from this direction, slightly to the side. Considering that as we move through the galaxy, not all stars fly with us. Some move slightly in other directions. These are old stars, red dwarfs. They move a bit differently. The conclusion of the work is quite obvious. We should observe the greatest flow of meteorites when Earth's motion combines with the Sun's motion. That is, when Earth flies with the solar system towards the solar apex, towards the constellation Hercules. And with the highest speed, naturally, interstellar meteorites should approach from there. And it turned out that we can generally expect the fall of interstellar meteorites in the winter seasons. In which parts of the globe? Generally, in the northern hemisphere of Earth, but the equatorial zone predominates. This is easy to understand. At the equator, Earth has a larger surface area than near the poles, where meridians converge. Simply, the surface area is smaller at high latitudes. So, the near-equatorial area of Earth's northern hemisphere receives the greatest flow of meteorites from interstellar space. With this work, I think we haven't yet fully drawn the necessary conclusions. For now, we only understand based on this modeling where they will come from, have come from, and always have come from, at least over the past hundreds of thousands of years, meteorites from interstellar space. The next step is obvious. We must search for remnants of such objects in existing meteorite collections. If they came and not all were destroyed, then probably someone sometime found them on Earth and kept them in their collections or donated them to scientific meteorite collection. Let's look in institutes, astronomical observatories, planetariums, mineralogical museums, and private meteorite collectors. Are there already gifts from the galaxy there? Are there foreign meteorites that, by isotopic composition, could differ from our native solar system gifts? It's such an obvious step that I wouldn't be surprised if in a few months articles start appearing from specialists in meteoritics, as we call them, with findings of the first interstellar meteorites that fell on our planet's surface. By the way, fresh news about meteorites. You remember on October 27, many people, especially from the capital and Moscow region, observed the flight of a powerful fireball. A fireball is such a bright meteor that glows, sometimes even illuminating the Earth's surface. I also had to comment on this news based on the first footage journalists showed me. Then, to me and other professional astronomers, it seemed like it was the fall of space debris because of how it flew, how it disintegrated. Its trajectory was close to the Earth's surface, flying along the surface. We decided it was likely a burned-up satellite or the last stage of a launch vehicle, something man-made. Now, enough data has accumulated suggesting it was most likely a natural object. Its speed was measured from many photographs. I think even radar was involved in these observations. It turned out it flew fast, at about 30 kilometers per second. Well, that's certainly not a satellite. Satellites don't fly at such speeds. They wouldn't stay near Earth if they flew that fast. Probably it was a natural object, quite large, maybe about a meter in size or several decimeters. Moreover, by tracing its trajectory, it was clear where it flew. It was quite far from the capital, somewhere from 400 to 700 kilometers north of Moscow, in the Novgorod region. But people rushed there and found remnants, meaning they found meteorites. A meteorite is what falls to Earth. A meteor is what flies and shines in the air. A meteorite is what has fallen on Earth. I don't know to what extent these found meteorites definitely belong to the one that flew on October 27. You know, there are actually quite a few meteorites on Earth's surface, but specialists say that most likely, these are its remnants. Moreover, they very quickly reached leading Russian meteoritics centers, like the Vernadsky Institute of Geochemistry and Analytical Chemistry in Moscow, the Ural branch of the Academy of Sciences. There, too, after the powerful meteor flew over Chelyabinsk in 2013, and then they found the meteorite. So now in the Urals there are also many qualified specialists in this field. and they went to other private museums, these fragments. So, scientists say the composition is completely traditional, a stony meteorite, a chondrite. They are commonly found. I can't say with 100% certainty that these are its remnants, that it fell on Earth's surface on October 27. There aren't precise data on this yet. What did they find? Well, how is it investigated? I understand. First, you need to make sure that the chemical composition of this body corresponds to meteorites. If it's an iron meteorite, a metallic one to be more precise, they also occur. Then its composition is about 95% iron, 5% nickel. But generally speaking, stainless steel smelted in factories has roughly the same composition. But in a meteorite, there are many other chemical elements. Their quantity is small, but they indicate that it's not factory steel but one that came from space. Meteorite hunters advise those who find a metallic fragment in the forest, field, somewhere by chance, to first check with a magnet before going to scientists or heading to scrap metal collection points. Don't be surprised, you wouldn't hand over a meteorite as scrap metal. You would ask for special instruments to determine its chemical composition, and a professional would tell you, this is iron left over from metal smelting, some slag discarded from a metalworking plant, or is it truly a cosmic visitor? After that, you can decide, keep it in your collection, donate it to scientists, or sell it. There are meteorite auctions. It's quite legal as far as I understand. The next stage is isotopic composition, meaning iron in which isotopes, in what quantity different isotopes, nickel or other rarer elements, how the isotopic composition is distributed. Then it will tell not just that it's a visitor from space, but where it came from, which part of the solar system. And generally, it's very useful information for scientists. In short, search for meteorites, watch for meteors, photograph their trails. Each of us can contribute to the scientific study of cosmic material. Every video that helps not only document the fact of a meteorite falling on Earth but also determine its flight trajectory, helps find remnants and understand where it came from, find its orbital parameters. It's a very noble pursuit, a scientific hobby always welcomed by scientists. I was pleased by one piece of news that in a way confirmed my old scientific publication. Long ago, I had a diploma student from India. Today, she is a well-known astronomer not only in India but internationally. We published a work related to the first stars born in our universe. We know the universe was born long ago, and the first generation of stars that formed then, 13 billion years ago, couldn't have anything in their composition except hydrogen and helium. Hydrogen and helium formed in the first minutes of the universe's life. Besides them, practically no chemical elements were born then. There was lithium in minimal quantities, so little you could say it wasn't there. The first stars consisted of hydrogen and helium. Then, after living their lives, they were very massive, exploded as supernovae. And in this explosion, more complex chemical elements were synthesized. The next elements of the periodic table, carbon, oxygen, nitrogen, iron, and sometimes possible transuranic elements that later disappeared. In general, the entire periodic table. And each subsequent generation of stars included the more complex chemical elements formed by the previous generation. So, era by era, billion years after billion years, each newborn star included increasingly complex and abundant chemical elements in its composition. 5% are other elements. We astronomers call them heavy elements, but they are heavier than hydrogen and helium. So, in the composition of stars, the percentage of heavy elements indicates which generation that star belongs to. And of course, we tried to find ever more ancient stars, those containing less and less heavy elements. Gradually studying stars around us, neighboring stars in the galaxy, we found some containing 10, 100, 1,000 times fewer heavy elements than in the Sun's composition. We even found some with 10,000 times less. But beyond that, the work didn't progress. With 100,000 times fewer heavy elements, we couldn't find any. Why doesn't our galaxy include primordial stars, those born long ago? The thing is, massive stars, of course, lived their lives quickly. But low-mass stars, red dwarfs, yes, they are almost eternal. Their life cycle lasts trillions of years. And if they were born back in the era of the first stars, they could very well have survived to our time within our galaxy. But we couldn't find them anywhere. And I and my student, it seems, understood the reason. You know, a relevant example. When everyone around you is sneezing and coughing, it's hard not to catch viruses. When all the stars around you are ejecting heavy elements, they explode. They send stellar wind from their surface into flight. It's difficult to remain completely uninfected by heavy elements, even if some ancient star in our galaxy had none at all. But after living several billion years within the galaxy, it must have been infected by these elements. That is, they must have landed on its surface. And today, looking at it, we detect these elements. And we made a prediction that we would never find stars in our galaxy containing heavy elements less than 10,000 times fewer than our Sun. And indeed, we never found them. Well, our galaxy isn't the only one. Recently, they looked at the neighboring galaxy, the Large Magellanic Cloud. It's a neighbor. Moreover, it's a satellite of our galaxy, but it seems to have lagged in its development, and there, the interstellar material has a more primitive composition, meaning fewer heavy elements than ours. And recently, astronomers found a star there that has 100,000 times fewer heavy elements in its composition than our Sun. Hooray! That was a good find. But in the end, well, we will find primordial stars. A paper just came out, it's in an archive, where astronomers have found a cluster of ancient stars. You see, you can only remain uninfected in a group where no one is sneezing. That is, in a group of primordial stars, no matter how much they eject elements from their surface, they can't throw out anything except hydrogen and helium. How was this managed? Generally speaking, in recent years, we find ancient objects mainly by the gravitational lensing method. That is, the object itself is so far away, somewhere there at the boundaries of the universe, that we wouldn't see it, but by chance, there is some massive galaxy or even a cluster of galaxies between it and us. And with its gravitational field, it focuses the light of that distant primordial galaxy, focusing it near us. And our telescope detects the light of that distant galaxy thanks to this gravitational lens that happened to be in the line of sight. And in this way, it seems, though it still needs verification, a cluster of the very first stars from the very first generation, in whose composition there are no heavy elements at all. The astronomers' prediction was confirmed. Water on dry exoplanets. Well, on some exoplanets, that is, planets belonging to other stars, water should be present because they formed far from their star, always living there. These are cold regions, and we find such water-rich planets. But it turns out there are some planets living close to their star, strongly heated by its light, where practically everything should have evaporated. Even before the planet itself formed, so close to the star, in the protoplanetary disk, there shouldn't have been water. It should have evaporated, flown away. Only mineral, refractory solid substances should have remained. Such planets have been found, usually called super-Earths or sub-Neptunes. That is, a planet by mass between Neptune and Earth, about 5 to 7 times more massive than our Earth. So, it turns out that living near the star and heating up from its light, they still demonstrate the presence of water. Where could it come from if they should have been purely rocky or iron? Sometimes astronomers are helped by laboratory chemists and physicists, and here, thanks must be given to chemists who simply modeled the conditions in which such planets should have formed. Namely, high pressure. This is, after all, a planet several times more massive than Earth. So there in the interiors, high pressure and high temperature should have been present. But it was assumed that there was nothing except mineral substance there, and some amount of hydrogen, which is always included with minerals. So it turns out that under high pressure and high temperature, several thousand degrees, the main mineral of Earth's interior, probably the interiors of those planets, is olivine. Those who have read Alexei Tolstoy's The Hyperboloid of Engineer Garin remember the olivine belt that promised great riches within Earth. So, olivine under high pressure, sufficiently high temperature, several thousand degrees, apparently breaks down into more elementary mineral grains, and then they enter into a chemical reaction with hydrogen, and in the process, water is essentially synthesized from hydrogen and oxygen, which is split off from the mineral. Calculations showed that in large quantities, such an iron-stony planet can form up to about 30% of its mass in the form of water. This water can reach the surface. Here, with some reproach to astronomers, that is, my colleagues, I want to remind that when it comes to the appearance of water on our planet, on Earth, astronomers usually say it came from space in the form of icy bodies from comets and maybe rocky icy bodies from asteroids. But geologists tell us, no, water came from Earth's interior. Volcanoes eject water vapor from within. It was born in the depths. And so, we astronomers and geologists couldn't find a common viewpoint. So, where did Earth's oceans come from? From space or from Earth's interior? These experiments show that geologists were partly right. Some amount of water could indeed be born, synthesized in the interiors of our planet and then reach its surface. Well, some astronomers are also right in some way. Probably, some came in the form of comet nuclei, asteroids at least. The isotopic composition of water in our world ocean quite closely resembles water we detect in the composition of asteroids. The latest news, and I'm glad to report this, concerns that the new telescope working at the Vera Rubin Observatory in Chile has proven to be truly excellent. It's just reaching its designed capacity. They've only just started operating it, but it's already giving us interesting discoveries and finds. The uniqueness of this telescope is that it's not just very large, with an objective diameter of over 8 meters, but it's also wide-angle. We haven't had such before. Unfortunately, all large telescopes that have worked until now, with objective diameters from 6 meters or even from 5 meters up to 10 meters. These are truly large telescopes. They had a very small field of view. Literally, they couldn't even photograph the full moon, only a piece of the moon. The size of their field of view was, literally, a few arcminutes, maybe 10 arcminutes. That's very small, like a pinprick in the sky. Therefore, they couldn't capture a large part of the sky simultaneously with good quality. Space telescopes are even worse. Worse in the sense that their field of view is measured in units of arcminutes. The Hubble Space Telescope, the James Webb Space Telescope have very small fields. They can't do such survey work. Finally, astronomers designed a very complex optical system consisting of 4 mirrors, and there are also correctors, lens correctors. Well, believe me, It's truly a very complex optical device, but now we have a large telescope with a large field of view. And here's one of its interesting finds. The central part of the Virgo galaxy cluster was photographed, a very well-known nearest large cluster of galaxies to us. There, the galaxy Messier 61 was discovered long ago. Actually, its very name Messier indicates that Charles Messier discovered it back in the 18th century and included it in his catalog. Previously, we knew it well, but the photographs were always small, only the central part of the galaxy, a beautiful spiral galaxy, but what's near it? Somehow we didn't pay attention to that. And now, a large photograph obtained by the telescope at the Vera Rubin Observatory showed that there's some hint of a tail appearing, almost imperceptible. But if you look, you can see a faint, hazy little tail moving away from the center of this galaxy. Of course, astronomers process this photograph mathematically to increase contrast. Those details that were lost in the bright images are now visible. And on this super contrasted image, it's of course not positive but negative. Actually, we're used to working this way. We love negative images. The images of the galaxies themselves are inserted so it's clear which galaxies belong to what. But you see the tail rising upward from Messier 61. Obviously, this is a stellar stream. How did it appear? Most likely, and we've become convinced of this by studying our galaxy, Messier 61 has consumed its partner or its satellite. Any large galaxy has satellites. We have several dozen, but from time to time, these satellites accidentally approach their mother galaxy, so to speak, and the gravitational influence, the tidal influence of the mother galaxy stretches them and practically destroys them. Only a stream of stars remains, which then fairly quickly mixes and stops being so prominently visible. But we caught this moment when the main mother galaxy Messier 61 swallowed its satellite. It was quite massive, by the way, and the stellar stream from it is still visible. This is a pleasant feature of the new telescope, which immediately allows for such images. Another feature of this telescope is its large field of view, allowing it to immediately discover many new cosmic objects. For example, on the image we're showing you, while they were taking it, 21 new asteroids belonging to the solar system were discovered. Each of them left 4 multicolored trails on the image. I'll explain why. Astronomers never photograph the way we do with our everyday cameras. Click and a color frame is ready. No, we take black and white images each time, but between the objective of the camera and the light receiving equipment, we place a color filter. So each time we get single color images. Blue, green, yellow, and blue, then combine them into color. But while the telescope took the same shot of the same area of the sky 4 times, each asteroid shifted slightly, moving through the solar system. Therefore, each of them left 4 of their colored trails on these images. But imagine, one photograph and over 2,000 new objects discovered in the solar system. Honestly, we've already discovered over 1.5 million asteroids in the solar system, but there's no such thing as too many. I really like today's news. You know why? You could say that over these past few years, astronomy has opened a new direction for its activity. There is planetary astronomy, stellar astronomy, and now there is interstellar astronomy. We, of course, knew that our solar system isn't the only one in the galaxy. There are billions of stars and billions of planetary systems in our galaxy, but they are so far from each other that mutual influence, as we thought, doesn't occur, and they don't exchange material. And here, please, since 2017, we have facts in hand, and soon, probably, there will be material that came to us from other planetary systems. Interstellar astronomy is born right now. That's all the news for today. Next time, more news. To not miss new stories about space, subscribe and hit the bell. Let's find each other in the cosmic vacuum. If you enjoyed this journey through the stars, make sure to subscribe, like, and share this video with fellow space enthusiasts. Your support helps bring more cosmic discoveries right to your screen.